Yesterday we learnt a very important thing in about optimization, that whenever there is a minimization problem, there is always an associated maximization problem goes on. This is a sort of duality mean and max, which is a persistent feature of optimization. And we had learned that even this presence of a maximization problem at the back of a minimization problem is quite natural even when you talk about 0%, 2% zero sum games. So, yesterday we had also learned an important fact that by solving the dual problem, we can a priori give a lower bound to the solution of the primal problem. So, thus the dual problem handling the maximization problem in the context of a minimization one makes a pretty good sense. And yesterday we had spoken about something called weak duality. So, today let us do something more. We had only spoken about duality in the context of inequality constraints, like if you remember yesterday's talk. So, now let us go and talk in the context of equality constraints also, that would allow us to construct duals for linear programming problems, semi-definite programming problems. And let us also keep on note, today's talk would be essentially more on duality. And of course, if time permits today, I will try to prove down the duality theorem, strong duality theorem for the convex programming case, but it is not necessary that it will be finished today, because there is a couple of things involved. So, let us first look at the more general convex optimization problem, CP in the more general form, where you are asked to minimize a convex function f subject to and A of x is equal to b, where A is a m cross n matrix. Never mind, you can even consider no problem, no probs or no problems if rank A is m, this is m cross n matrix, that is full rank. You may or may not, but in general it is, this condition holds. If A is a n cross n matrix, no problem if this, and B is in R m. So, this is quite a general constant qualification. I would let you as a homework if I add x element of x. So, how do I construct the Lagrangian in this case? That is the thing. So, now how do I express this? I can express Lagrangian now would have x lambda, the Lagrangian multiplier vector associated with this, and the vector associated with this. Sorry, because I have taken here this to be m, I would just change this to make it look much more authentic, k cross n, and this would be k. Actually, when you write on blackboards, life is simpler. So, now you have to have a mu. Remember that associated with the equality constraint, the mu has no sign. So, x comes from R n, lambda comes from R m plus, which consists of the Lagrangian multipliers of inequality constraints, and this is the Lagrangian multiplier for the equality constraints, it comes from R k. So, it is usually written as f of x, you can place y and z also, I am just taking, you might think okay, come on guy, you have taken y here, does not matter, y this is just a change of notation because we are in a more general setup. So, here you can also write A x minus b, does not matter, whichever way you take it, is equality constant. So, this is my associated Lagrangian in this case. So, now this setup defines quite a good class of problems. So, how do I compute the Lagrangian or the Lagrangian dual of several type of optimization problems? That would be our first goal today. So, let us consider the linear programming problem in the standard form, because very soon we will indulge ourselves in the pleasures of linear programming. Linear programming problem in the standard form. So, again I would like to repeat our goal here. The goal is twofold: provide examples of how to construct Lagrangian duals of two important class of convex optimization problems. One is the linear programming problem, another is the semi-definite programming problem. Now, let us look at the linear programming problem in the standard form. So, if I want to write it more explicitly, like the form that I have written for CP, so I should write in this form. A is again the k cross n matrix of full rank whatever. So, I can rewrite as so this is my f x C of x minus x I less than equal to 0. So, these are the inequality constraints and this is the equality constraint. So, once I know this little fact, now I would like to imitate and write down the Lagrangian by putting specific f and gi's. So, L x lambda mu is this, let me see, is C of x plus lambda 1 minus x 1 plus lambda m minus x m plus mu. Okay. So, you see it is quite simple to do the job. Now, once I know the Lagrangian, how do I write down the Lagrangian dual in this particular general case? That would be the second step. So, my first step would be to construct a function theta now would have be of two vector variables lambda and mu, which is again the same thing, infimum over all x in Rn of L x lambda and mu. Now, the dual problem for this case max of theta lambda mu, where lambda is element of Rm plus and mu is element of Rk. So, these are the constraints. So, this is my dual problem. Now, it is slightly complicated. So, now if I want to write down the dual problem for this standard linear programming problem, this is often called LP or LPP, linear programming problem in the standard form. Now, I want to construct this function Now, in this particular case, in the context of a linear programming problem, what would be theta lambda mu? Does it have a specific form? That is the thing that we would like to figure out. Now, let us look at it very carefully and see what is therein. So, if I look at it very carefully, let me observe one thing, that Lx lambda mu is written as now, I will club the x things together. So, I can write this as C minus lambda into x plus mu b minus mu times a x. This will be as follows. Then again mu b minus mu a x. So, see, I am gradually coming towards a neater form. Now, this by simple laws of linear algebra can be written as, or of just transpose. So, I am able to write this as now, I claim that I am making a following claim. Let us see how can I the only way. See, if I want to minimize this function over whole x, it has to be finite at least. The only way to have Lx lambda mu finite, right. If I take the minimum over all x, it will not be of much important unless the only way I have, see, first of all I need to have this finite in order to have a decent or a proper dual objective function. So, is to have or I will just remind that this actually means, I just inadvertently did not do it because it is so common, this form, right. So, this is my claim. So, let me see how good is this claim. Is it a correct claim or a wrong claim? I have no idea. Now, suppose this is not 0. So, there must be at least one component which is not 0. So, there exists j such that C minus lambda minus A transpose mu, the jth component is non-zero. So, let us assume it is done without loss of generality. You could have assumed it to be negative and give a similar sort of argument. Suppose this is strictly bigger than 0, then then set xj strictly bigger than 0 and xi equal to 0 if I is not j. Then what I can do is I can keep on increasing the value of xj, keep on increasing the value of xj, make it so big and big and big and big that this function just keeps on blasting up and go towards infinity. Thus, as xj plus infinity, because this is, even if it is negative, it will be just suppressed once this becomes very large. So, it blows up. So, it is not finite at all. So, which means that if I want to minimize, I can show that I can move along one line and and this is unbounded both ways. So, as xj tends to, I should have minus infinity, xj tends to minus infinity, this thing also tends to minus infinity. See, this thing also tends to minus infinity, I am writing, making a mistake. Because now this, if you take the inner product, then what you will have is that C minus lambda minus A transpose mu, if all the xj's other than, all the i's, xi's are 0 other than xj, this will only lead to the value is this C minus lambda minus A transpose mu j xj. Now, suppose xj is negative and this is positive, then I can keep on. So, this will be negative. So, I can go make xj go down, 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 down as much as I like, and so this whole thing would go towards minus infinity. So, this infimum will not have a finite value. So, which means if a similar argument can be said, if this is strictly less than 0, then you can put this to be strictly bigger than 0 and go ahead. So, it shows that if I move now for this particular class of xj's, if I keep on, I am generating a sequence which is along which the function value goes down to minus infinity, this function value. So, this cannot have a finite minimum. So, there cannot be a finite sort of dual gap function, dual function. So, but if I put this to be 0, it is immediately finite, it is mu b. So, if you take infimum over whole x, all the x in R, and that answer would be mu b. So, inf of L x lambda mu, which is theta lambda mu, is equal to mu b if A transpose mu plus lambda is equal to C and lambda is in Rm plus. Assuming that A is m cross n matrix, I am just writing Rm plus without even telling you anything. So, you might just get angry, or what is this? In our case, let us take this to an m cross n matrix, right. So, we have done a calculation. So, now what is the dual problem? Then I have to, the dual problem is to minimize B mu over mu and lambda such that, so sorry, not minimize, maximize the dual problem, maximize mu and lambda such that A transpose mu plus lambda is equal to C and lambda is greater than equal to 0, that is, it is in Rm plus. This means Rn plus. This is some, because I have taken x is in Rn plus and lambda are the Lagrangian multipliers or the multiplier is associated with x. So, that this lambda vector is in Rn. So, this will be in Rn plus, which is lambda greater than 0. Sometimes lambda in the literature you will always see. So, this is that in place of mu people are writing y, in place of lambda people are writing s. That we can do specifically. We will adhere more to the linear programming community when we will go on to the special set of things that we will study, which I would like to call the pleasures of linear programming. And we do it because it is a subclass of convex programming and it is very, very important. Now, I will give you a homework. The problem is the linear programming problem. Minimize Cx, Ax is bigger than equal to b, x greater than equal to 0. Another problem is to minimize Cx, Ax. Now, Ax greater than equal to b here means component wise bigger and component wise lesser. Now, the question is construct the Lagrangian dual for these two. So, the homework is follows: construct So, you will tell me, or rather I will tell you possibly in the next class what are the answers of these. So, now we go to a more general category of optimization problem. That is SDP, the semi definite programming problem. So, you know our theater is in Sn, the space of n cross n symmetric matrices, and the cone that is useful here is Sn plus, the cone of positive semi definite matrices. They are symmetric n cross n and sim PSD n cross n, right. Of course, each AI is in Sn and x should be in Sn plus. Rn plus is now replaced with Sn plus. So, this we have already discussed earlier as an important class of convex optimization problem, a semi definite programming problem, or colloquially known as SDP. SDP, as I would like to stress once again, that is the hottest area of current research, not because it is something novel, because your decision variables are no longer vectors, but matrices, but it has huge application. Many problems are of this form, and further for this class of problems you can write down a polynomial time algorithm, which is a very, very important thing. And it is very important to notice again that SDP problems have recently shown a great promise in handling non-convex global optimization problems. You can actually consider, for example, a polynomial optimization problem, which is a very hard problem, and then it can be shown as had been shown by Lazaire very recently in this particular decade, in this not decade, I would say in the previous decade, in 2002 I guess, that give me a problem which is a polynomial optimization problem, and I can write down a sequence of semi-definite relaxations of that problem, and I can solve the semi-definite relaxations by standard techniques which are now well known, including a software, and the sequence finally goes and converges to the actual solution of the polynomial optimization problem, to one of the actual solutions. So, this is a very big move, because he got the Lagrange prize for this, because here we are telling that, look, here is a very difficult non-convex optimization problem and it is so difficult to solve it, but okay, instead of trying to find a crude algorithm about it, you have a very good approximation which can be whose approximated components can be easily solved, and then you finally can get a quite a very robust, in some sense, approximate solution. So, what it means that even when my problem is a non-convex polynomial optimization problem, I am actually still in the convex world, and that is why convex optimization is such an important area. Now, the question, as I told you earlier, that this problem is not just a linear problem in matrices. It is not just a linear programming problem in matrices. It is a general convex problem since, of course, those who know Sn plus is not polyhedral. Can you again think of a reason why? Now, the question is, do this problem have a dual? I can imitate what I have done for the other case and write the following. I can now construct a Lagrangian. So, how do I construct a Lagrangian associated with the SDP problem? Here I will not use, I cannot explicitly write down the inequality constraints, these constraints in form of inequalities. So, I will do the following: x where lambda is in Sn I equal to 1 to m. So, this x which ai's are in Sn. So, this is also in Sn. This can be written as C of x plus lambda 1 B 1 minus A 1 x lambda m B m minus once I have constructed this, the clever trick is that I am not including this constant, which is a hard constant, that x has to be positive semi-definite into this framework, into the Lagrangian framework, for how to in the formulation of the Lagrangian, because I cannot write it down in form of inequalities. I can write down by what is called the Loener ordering. I can write down like this, but then I at least have no idea how would you bring in that as an inequality constant here. Possibly you can by multiplying with some PD matrices. So, but we are not going to handle this way, but we will allow you to think over how to do it. You can do it, but it is not apparent because you cannot write down the Lagrangian, cannot write down this in a easy form of inequalities as you have done for this case as we have done for the LP case. Okay, somebody said, okay, let me tell you one thing, we can just possibly extend this Lagrangian a bit. Okay, let me do, I will just write L x s lambda. Well, lambda is a vector, right. I am writing this lambda in form of like almost looks like a matrix, but I should write as lambda. The lambda is a vector because it is nothing but lambda 1, lambda 2, lambda m. No, sorry, it should not be, not in Sn, it should be in Rm. But Rm. Now, I can now construct another Lagrangian. I can construct another Lagrangian. This is in Sn, this is in Sn plus, and this is in Rm. Let us see, this we will construct like this, almost an imitation for the linear case. Plus the remaining same part, lambda 1 into now, once you know this, you can again say that okay, I can either construct my dual function as theta naught lambda by minimizing L x lambda over x element of Sn plus, or I can construct theta capital S capital lambda, and then of course maximizing. Then my dual problem then is to maximize theta hat lambda over lambda. This is my dual problem. I can also write this one as not mean, I should write inf, but okay, it does not matter, mean and inf things you gradually understand that if the mean, if there is no point where the minimum is achieved, then of course that is what is the infimum. Here my infimum is not over Sn plus, but over Sn of L x s lambda. Now, let me take the second formulation and then try to see how do I compute this, what is this. So, in order to do so, I again write down like I did it for the linear programming case. I am rewriting this fact. Now, I will club lambda 1 b 1 lambda m b m together, and basically I will have lambda b, which you could have written as mu b also, does not matter, minus lambda 1 a 1 plus lambda m a m. I want to again remind those who have forgotten what is the inner product between two symmetric matrices, it is trace of x y. So, I can again write lambda b plus c minus s minus lambda 1 a 1 lambda m a m. See, this symbol is called the Loener's ordering. This simply means that x is positive semi definite. obviously you do not have to bother too much about a name. Now, I leave it to you to prove that if this expression so theta s lambda is finite and is equal to lambda b if and only if this is 0. So, by the linear programming type of argument, your dual problem is max of b lambda subject to C So, this C minus this thing is 0. So, C minus this thing is equal to S and S is in Sn plus. Okay. So, my dual problem in the dual variable, I can also write the dual problem as follows. So, as per linear programming, this is what happens. Of course, I can write it as either, if I can write it like this, that is lambda 1 a 1 or you can write it as this last this sort of inequalities are called linear matrix inequalities or LMI, has a lot of applications in electrical engineering. So, you see we have learned how to construct our duals for both the linear programming case in the standard form and 2 are kept for homework and the case of semi-definite programming. Okay, suppose I want to take this formulation, what would happen? That is the question. So, if I take this formulation, that is I have to take in power x element of Sn plus, let us see what would happen. So, in this case it can be written as b into lambda lambda b. Now, you see x is element of Sn plus. Now, you can argue that unless this is equal to Sn plus, I cannot say anything. Now, x is in Sn plus and okay, if I look into the formulation, now x is now in Sn plus, I have to minimize over that. So, when do I have a finite value for this? Now, you see that if this is in Sn plus, then this is greater than equal to 0, which means if C minus lambda 1 a 1 lambda 2 a 2 lambda m a m is in Sn plus, then if you have 2, this is a very standard result, you can figure out yourself. So, if A is in Sn plus positive semi definite and B is also in Sn plus, then trace of AB is, of course, it is not a very standard result, I just said it is a standard result. This is something linked to something called self duality of the cone, which is not immediately obvious, but we will figure this out in detail when we study semi definite programming. There is the part of the course is focused on semi definite programming. So, and we will see how much helpful semi definite programming is to many areas, when it can enter even non convex problems, break the bones and non convex problems and give us something. So, now if this is in Sn plus, and because x is in Sn plus, this would be greater than equal to 0. So, if this is in Sn plus, I would have Lx lambda to be bigger than B of lambda, because this is bigger than equal to 0, right. Now, what is the infimum value? See, if I put this equal to 0, then Lx lambda is B lambda. So, in fact, this is what is true. So, I have inf over x element of Sn plus if so, if this is true, which is exactly what we were dealing. So, this is bigger than this, but at the end I want an equality, I always wanted an equality. How do I get an inequality? Let us ponder. But x is in an element of Sn plus. So, when I put x is equal to 0, the 0 matrix is also in Sn plus, this is positive semi definite. When I put this is equal x is equal to 0, then I get back the value B lambda. So, B lambda is one of the values of Lx lambda obtained as I move x through Sn plus. So, which means finally I get inf of Lx lambda with x element of Sn plus to be B lambda if this holds. So, my dual is again to maximize B lambda such that C minus lambda 1 A1 minus lambda 2 A2. So, I showed that in both ways you can come to the same conclusion. So, any way you can proceed. Again I am putting the Loener ordering. We have no time to prove the strong duality result today, and we will end the talk today here, and in the next lecture we would talk about the proof of the strong duality theorem and show that if the Slater condition does not hold for a convex programming problem, we can give examples where strong duality fails. And for non-convex problems, strong duality does not hold. See, this story of constructing Lagrangian dual is irrespective of whether the problem is convex or not, but here since we are concentrated on convex problems, we will show that even for a convex problem, if Slater condition fails, the strong duality goes. We will have examples even for semi definite programming problems. Thank you very much.